Think of a compiler as a kitchen that turns a recipe source code into a tasty dish machine code. The first chef in the kitchen is the lexical analyzer, also called the lexer. Its job is to break the long string of characters into bite-sized words called tokens, like ingredients. Without this step, the later chefs, parser, optimizer, code generator, would have to understand every single character, which would be slow and confusing. The lexer gives structure. It tells the parser where numbers, identifiers, operators, and punctuation start and end, just like a grocery list tells you which items you need to buy. In short, lexical analysis is necessary because it simplifies the huge raw text into a clean, well-defined stream that the rest of the compiler can work with efficiently. A token is defined by a pattern that tells the lexer what strings belong to that token. These patterns are written with regular expressions regex, which are like simple recipes for matching text. For example, the regex a to z underscore followed by 0, or more of a to z a to z0 to 9 underscore, describes an identifier. It starts with a letter or underscore, followed by any number of letters, digits, or underscores. A number could be described by 0 to 9 one or more times, optionally, a dot, followed by 0 to 9 one or more times, meaning one or more digits, optionally followed by a dot, and more digits. Formally, a regular expression is built from basic symbols characters using three operations: concatenation. A B means a followed by B alternation, a bar B means A or B, and clean star a star means 0 or more repetitions of A. These operations correspond exactly to the ways we combine simple words to make more complex ones, which is why regular expressions are perfect for spelling out tokens. To turn a regex into something the computer can run fast, we first build a non-deterministic automaton, NFA, using Thompson's construction. Imagine each tiny piece of the regex as a Lego block that creates a small machine with a start state and an end state. By connecting the blocks according to concatenation, alternation, and star rules, we get a big NFA that accepts exactly the strings described by the regex. However, an NFA can be in many states at once, which is hard to simulate directly. The subset construction, also called powerset construction, converts the NFA into a deterministic finite automaton DFA, where each DF, a state, represents a set of NFA states. The start DF a state equals epsilon closure of start NFA. For each DF a state S and each input symbol a compute move of S, an equal set of NFA states reachable from any state in S. On a then take epsilon closure of that set, this becomes a new DFA state, or an existing. Repeat until no new DFA states appear. Mathematically, if delta NF, a colon Q underscore N times sigma maps to 2 to the power of Q underscore N, is the NFA transition function, the DFA transition function delta DF, a colon 2 to the power of Q underscore N times sigma maps to 2 to the power of Q underscore N, is defined by delta DFA of S, a equals epsilon closure of union over Q and S of delta NFA of Q. The resulting DFA accepts the same language as the original regex, but it can decide the next state with a single table lookup. There are two main ways to run a DFA inside a lexer. In a table-driven scanner, the DFA is represented as two large tables, one for the next state indexed by current state and input character, and one for the token type to emit when entering an accept state. The lexer then becomes a tight loop that reads a character, looks up the next state, and repeats, much like using a GPS map stored in a matrix. This approach is fast because the CPU only does array accesses, but it can use a lot of memory for big character sets. In a hand-coded scanner, the programmer writes if-else or switch statements that mimic the DFA. This can produce smaller code and allow custom shortcuts, for example fast path for a SCII letters. However, it is more error-prone and harder to maintain. Modern lexer generators Flex and JFlex produce table-driven code automatically, while some performance-critical projects like JIT compilers may handwrite the scanner for ultimate speed. When several token patterns could match the same piece of text, the lexer must decide which one to choose. The longest match rule says red characters. Until no pattern can extend further, the longest possible string wins. Think of it like reading a road sign: you keep going until the sign stops, you don't stop halfway. If two different token types match the same longest string of priority, often the order in which the rules are written breaks the tie. For example, if matches both the keyword rule if and the identifier rule A to Z or underscore, followed by a to Z or A to Z or 0 to 9 or underscore repeated. Because keywords have higher priority, the lexer returns the token if instead of an identifier. Implementations enforce this by scanning with the DFA while remembering the last accepting state and its associated token. When scanning stops, the lexer outputs the token attached to that last accept state. A lexer not only finds tokens, it also watches for things that do not belong to any rule. When DFI reaches a state with no outgoing transition for the current character, an error is reported. Good error handling provides a clear message like illegal character at sign at line 12, column 5, and then tries to recover so scanning can continue. Common recovery strategies include panic mode, skip characters until a known synchronizing token, for example a semicolon or a newline, is found. Insertion, pretend a missing character like a missing semicolon was there and continue. Deletion, ignore the unexpected character and keep scanning. The lexer usually records the line and column numbers by counting newline characters, making the error messages user-friendly. These mechanisms let the rest of the compiler see as much of the program as possible, even when the source has mistakes. A DFA can contain many states, many of which behave the same way. Minimization merges equivalent states, producing a smaller automaton that runs faster and uses less memory. The classic algorithm, Hopcroft's algorithm, works by partitioning the state set into groups that cannot be distinguished by any input string. Initially, states are split into accepting versus non-accepting groups. Then the algorithm repeatedly refines groups using incoming transitions until no further split is possible. The result is the smallest DFA that recognizes the same language. Optimizations for high-throughput scanning also include character class compression stores a single transition for a whole class like a to Z instead of 26 separate entries. Sparse tables use a default state for rare characters to save space. Inline fast paths check common cases such as letters for identifiers with simple code before falling back to the table. These tricks make the lexer capable of scanning millions of lines per second, which is crucial for large projects and interactive tools like IDEs. The lexer's output is a token stream, a sequence of pairs token type lexeme together with location info line column. The parser consumes this stream to build the program's syntactic structure parse tree. Often the lexer also interacts with the symbol table. When it sees an identifier, it may look it up or create an entry, so later phases semantic analysis can quickly find its type or scope. Some compilers separate concerns. The lexer only returns the raw identifier string, and the parser adds it to the symbol table when it sees a declaration. Either way, the contract between lexer and parser is simple: a steady flow of tokens, which allows each component to be developed and changed independently. Many real-world tools automate the whole process of turning regex rules into fast lexical scanners. Lex and its modern clone Flex read a .l file containing regex to token mappings, generate C code for a table-driven DFA, and compile it alongside the parser. JFlex does the same for Java, producing a Java class that implements the java.util.scanner interface. ANTLR goes a step further. Its grammar language lets you write lexer rules and parser rules together. ANTLR then generates both a lexer as a DFA and a recursive descent parser. These tools illustrate the theory in practice. You write human-readable regular expressions. The tool builds an NFA, converts it to a DFA, minimizes it, and gives you ready-to-use code. Case studies show that using Flex can scan about 30 megabytes per second on a modern CPU, while handwritten scanners may squeeze a bit more speed at the cost of development time. The takeaway is that the formal constructions we discussed are not just academic, they power the everyday compilers you use.